Hi, today we are doing the second part of our section 8.1, which is sequence and series, the very first lesson that we've done. But this part of 8.1 we're just wrapping up, and we're actually going to look at the series part and a few things in the notation that you need to be aware of. So in a series, we're going to be using the sigma notation, which is a Greek uppercase letter, and we use it to signify that we're going to sum or add some things together. The symbol and the notation looks like this, and so you have that sigma, and then there is an index or a letter right here that's the index. It's equal to a number, and that number is the lower bound. In other words, that's the number you start calculating from. Then on top of sigma is another number, and that's the upper bound, and that's where we end our calculation at. In front of the sigma will be a sequence, and so all of these pieces together make up sigma notation. And there are some properties that we have on our note sheet that is right here. And these properties are just ways to go about the calculation and make it a little easier. So for instance, this sigma has just a constant number, no variables with it. And then this one is a constant number with a sequence with it. And it says we can pull the C out in front and we can evaluate the sequence. Down here we have where we have two different sequences. So it's not just a number A and B, but it's a sequence we're calling A and a sequence we're calling B. And so instead of making this bigger calculation here, we can evaluate sequence A and get its sum, and evaluate sequence B and get its sum, and then just add them together at the end. It can make the math by hand a little easier. Over here, same thing is true except it's subtraction. Do remember, subtraction is order specific, so we always need to evaluate the summation of A minus the second one, which is the summation of B. So we're going to work through these problems right here and wrap up everything you need to know about the beginning of sequence and series. So the first property is a constant number. And so the property says if it's a constant number, you can take the constant number by whatever your upper bound is. And so if we just worked out one so you could see if the constant was 2 when I was 1 and I is 2, and we would go all the way out to when I equals 3 and I equals 4. And so we would calculate that each time. You're just going to get the number 2 because there's no variable. And so when I is 1, it's a 2. When I is 2, it's a 2. When I is 3, it's a 2. When I am 4, it's 2. All of these have a 2 in common, so we really could pull out a 2 and leave me with 1 plus 1 plus 1 plus 1, which is 4. And so 2 times 4 gives me my 8. Well, think about this. The upper bound was 4, and that's what we were multiplying by. The constant number was 2, and together the summation is 8. So one thing you need to remember when you're talking about series is series are connected by plus signs, not commas. If you see a comma, you're talking about a sequence. So these were the other properties. So if there is a C and a sequence, C being a constant, you can pull the constant out in the front, evaluate it for the sequence, and then multiply by that constant at the end. And here are the two where we separate it out. So these are handy properties to note, just because they can make, if you're doing a problem like this by hand, a little easier. So in the first set of problems, we're expanding, and that means we're listing out all the terms, we're connecting them by a plus sign, and then we're doing the math to get a final answer. So my lower bound is 1, my upper bound is 4, the sequence is 3i. So when I is 1, I do 3 times 1. When I is 2, I do 3 times 2. When I is 3, I do 3 times 3. When I is 4, I do 3 times 4. So 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, 3 times 4 is 12. So that's just working it out by substituting the numbers in and making our values happen. And so then when I add all of these up, I get a summation of 30. If I use the property, then because 3 is a constant, I would pull the 3 out in front, and then I would evaluate from 1 to 4 with an I. So when I is 1, it's 1. When I is 2, it's 2. When I is 3, it's 3. When I is 4, it's 4. 4 plus 3 plus 2 plus 1 is 10. 3 times 10 gets me that same 30. And then we can always check on and kind of back up our answers on the calculator. Please understand that you will be doing a lot of these things by hand and with symbols and with your sequences, and it's not always just a matter of punching it in the calculator, but it's always nice to be able to check and see if what you're doing is correct. So if I do this same problem on the calculator, there are a couple of ways to get to the sigma notation. I typically just do alpha window and summation is choice 2. So you can pick that and you get your template. So since we're using the calculator, I'm going to make my index letter be X. Your index letter should match up whatever you're using in your sequence, but it could be any letter. And then I'm going to have a lower bound of 1 and an upper bound of 4. And then I'm going to put 3. And because I used an X as my index variable, I need to use an X in my sequence. And so when I put that in, it's going to do that same evaluation we did right here, and it's going to get the same 30 that we got. So you can use that as a way to check yourself. You can also do math 0, and that gives you the template as well. So there's more than one way to get it. I typically use the alpha menus because even if I forget something, I can go alpha y equals, and I can just arrow over and hop through the menus if I forgot where something is at that I need. So that can be helpful. All right, so now we know how to do it on the calculator. So if you want to put it in your notes, the alpha window option is for the number 2 summation. You could also do math 0. All right, so now we're going to do the next one. So you can see on this one with the calculator, I did go ahead and change it all to X's so you could just see what that looks like. So if we're evaluating the next one, we're going to start with a lower bound of 3. You don't have to start bounding at 1 or 0. It's going to be a lower bound of 3. It's going to end at 6. So that means we're going to calculate when I is 3, when I is 4, when I is 5, and when I is 6 would be my upper bound where I'm stopping. So then I would go in here and I would say 3 squared is 9 plus 1 is 10. 4 squared is 16 plus 1 is 17. 5 squared is 25 plus 1 is 26. 6 squared is 36 plus 1 is 37. When I add it together, I can do 30 plus 20 plus 10 plus 10. Then I could add the 14 and then the 6, or you can add it traditionally and get your 90. So that's just crunching the problem and working it out just like we would do any old math problem, evaluating it for each of the index numbers. If I use the property, I would say the first one, so this would be my A sequence and this would be my B sequence. So I would go from 3 to 6 at 1 and I would go from 3 to 6 at I squared, and then I would add those results together at the end. So when I do 3 to 6, that's 4 numbers between 3 and 6 ending at 6. And so I would do 1 times 4 using actually the constant property. And then I would do 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36. So when I add these numbers up, I get 86, and I can add it to the 4 that I already have, so I get the same thing as a 90. And then once again, I can go to my calculator if I want to double check, and I'll do, this time I'll use the math 0 option, and then I will do X equals, oops, if you hit the equal, do you see what happened there? It popped up to the top. So you do have to pay attention to where you're doing that. And I would do 3 for my lower bound, 6 for my upper bound, and then in parentheses I would do 1 plus X squared because my index letter is X, and that's going to get me that same 90. So you can always just double check as you're working through some of these. Cool. All right, so I hope you're doing well right now and you're all on target with me because this Sigma stuff is not too bad. All right, so right now we have another Sigma notation, and it is a doozy because we're doing factorials and we know how big factorials can get so fast. So I have I is 0 goes to an upper bound of 8. So that means I have to do right in here where you see your I, 0 factorial, 1 factorial, 2 factorial, 3, 4, 5, 6, 7, all the way up to 8 factorial. So we're talking some really big numbers. So remember our fun facts are 0 factorial equals 1, 1 factorial equals 1. We learned those last time, so we actually have a 1 here and a 1 here. And so then you can see I went ahead and calculated these out so you could just see how big and fast they went, so I didn't take time actually calculating. And then when I added all those fractions together on my handy dandy calculator, I got this amazing decimal that should kind of look familiar. I thought this was kind of a fun one because it's really close to E. So this is an approximation that's getting us really close to the number E. Remember, E is a transcendental number, so it is a letter that represents a number, so it's a constant value. It's not a variable. So sometimes people forget about that. So if you are doing it on your calculator and you're trying to put factorials in on your calculator, if you go to the math menu, you can go over to probability. You can down to choice 4. and you can get it there. There are some other ways on the calculator to get the factorial, but that's probably, I think, about the easiest. So like if I wanted to do 5 factorial, I'd press the math button, and then I go over to probability, and you can see the exclamation point is number 4. And so, wow, that would be really big because that's going to take the 90 I got in the last problem and do a factorial with it, which is an overflow, too big to handle. So if I were going to do, let's say, 5 factorial, I press 5, I go to the math menu, I go over to probability, I pick choice 4, so you can see it's 5 factorial, and that gives me 120 because that would be 5 times 4 times 3 times 2 times 1. And we worked that one last class period. All right. So just remember a few reminders here. The lower limit does not always have to be 1. The index could be anything. The index letter does not always have to be I. It could be anything as well. So just a little note there. Now let's shift gears a little bit and let's talk about the definition of a series. The sum of the first n terms of a sequence is called a finite series. So a sequence will be connecting everything with a comma, and then we're going to come in and find the sum of part of that sequence. And so that's a finite series. Or we also call that partial sums. So for instance, here's my sequence. It goes on forever to a sub n. And then my summation is going to go from 0 or from 1 to n because that index number was 1, and wherever or whatever it happened to be. When we do this, when we say, here's my one that goes on forever, but I'm going to find the finite sum or a part of it, then we use this notation S sub n. And that means n partial sum. So you do have to be very careful, right? Last unit or last section, well, this section at the beginning actually, a sub n represented a place in the sequence. S sub n represents the sum of a part of the sequence. So that may be actually in your directions. It might say, here is the sequence, find S sub 5, and you would need to know that that means you're finding the sum of the first 5 terms. The sum of all the terms of the infinite sequence is called an infinite series, and that means we're going to infinity. So when we're going to infinity, we have to use the S instead of an S with a subscript. S with a subscript is a part of it, where S is the whole thing. And so in essence, what we're doing is looking at where or what number this series might converge towards. The downside is you cannot use your calculator options here. You cannot put infinity in the sigma notation. It is unbounded and it won't calculate it. So sometimes then we just have to calculate a few terms to see what they merge towards. So the difference in part A and B on 2 when we're finding the sum is we're just going from 1 to 3. So that means we're finding the first 3 terms. Lower bound is 1, upper bound is 3. So I plug that in for I. 1, 2, 3. I get the fractions 3/10, 3/100, 3/1000. The equivalent, I always go to decimals on these because sometimes it's easier to see. So 0.3, 0.03, 0.003. And when I add all of these up, I get 0.333. So now that's not the fraction 1/3 because that 3 isn't going on forever. So how you would write this is we are finding the third partial sum. So we would say S sub 3. And we could do the decimal or we could do the fraction equivalent if you so wanted to do a fraction. So that's the idea of how you would go about finding one when it's going to infinity. You've got to start somewhere and look at a few terms. So notice that this next one actually goes to infinity. It's the exact same sequence. So nothing new there except instead of stopping at 3, we would keep going. Well, we know that pattern now. We know at 3/10 it was 0.3 and then it was 0.03 and then it was 0.003. So if I go 10 to the 4th, it's 0.0003. And if I go 10 to the 5th, it's 0.0003. And I keep adding the zeros. Well, if I think about adding all of these numbers up, then I get that really frequent or familiar repeating decimal, 0.33333, which its most exact answer then would be 1/3. So we could say the sum, notice no subscript, because we want to see what is it converging toward, what is the whole sum, is about 1/3. So that's the most exact form. Sometimes if you're looking for a pattern, you can use your calculator to help you just a little bit. Like if you didn't remember for whatever reason that was 1/3, you could do 0.333, fill up that window, get as many digits out there as you can, and then do your math frac button, and it will convert it to a fraction if possible, and it does. It's 1/3. So we're just kind of tricking the calculator there. And so that's what this note here about is doing math frac was just another way to come up with that fraction 1/3. So maybe it's a repeating decimal you're not familiar with. That might be a technique while you're working through the problem. All right, part C. We are going to infinity again. Here is my sequence. Lower bound is 1, but we're finding s sub 3. And so this is what I meant by knowing the notation, because it may use notation to ask a question. So what this s sub 3 means is find the third partial sum of the infinite series. So it goes on forever, but we're only going to add the first 3 terms. So if we decided to use the property, we could pull the 4 out here. We could go in with I is 1, 2, and 3 right here, which gives me these 3 fractions. So to put fractions together, I would get a common denominator. My common denominator is going to be 8, so I multiply 2 by 4, so that becomes negative 4 on top. 4 I'd multiply by 2 to get 8, so that would multiply 2 on top. And 8 I didn't multiply anything by because that is my common denominator, so that's just minus 1 on top. So I put all these together, I get minus 3, and then I can simplify with that 4 on the outside, and it becomes negative 3/2, which means the sum of the third partial terms, or the first 3 terms, is negative 3/2. So this is me working through using the sequence in the summation, and this is how we would write our answer at the end, the third partial sum. Notice it states that in the question. It's always a good idea to state your answer in whatever direction it takes you in the question. The last thing we're going to do, and we're almost finished here, guys, is write the sum using sigma notation. So when you see a sequence like this, so 3, negative 9, positive 27, negative 81, positive 243, negative ... we know that this is going on forever because of the ... at the end, which makes this a infinite series. Push that up just a little bit. And so when we have this infinite series, then we would be looking for patterns. So the first thing I hope you recognize after our time last time is you see that alternating sign. And so you know you got to have that negative 1 to some power in your sequence. And we know it begins with the second term, so that means the power has to be n plus 1. And then I would add that to my sequence, and I would look for my pattern. What is the number pattern for 3, 9, 27, 81, 243? That's on our list from last time. So here's what it looks like. ... means it goes forever from 1 to infinity. This is the part that gives us the alternating sign that begins with the second term. This is the part that gives us the numbers in our order. And so all together, this is our sequence. And probably I would say I would come in here maybe, and since it's part of it, probably go ahead and do that. Okay? So just remember, a sequence describes something. So you're describing the behavior, so we had to describe the alternating sign behavior. We had to describe the number behavior. So here's the last one. We have 7 over 1 plus 1 plus 7 over 1 plus 2 all the way out. Notice the ... dots are not at the end. They're in the middle. And then we stop here at 7 over 1 plus 10. So that means we have a definite ending amount in this particular series. So when we set up our sigma notation, because we're writing, this last one said to write it in sigma notation, I have to figure out how many terms this is. And that big clue is right here at the end. That was 10. So there'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that means my lower bound is 1. My upper bound is 10. And then you could use I equals 1. Remember, you can use any letter you want. You just have to be consistent with your letter in here. So then I would say 7, because you can see there's no change in the 7s on top. And then 1 is then 2 is being added, then 3 is being added, all the way to 10 being added. So that's where my n is on the bottom. So in the middle of the series, it means the dots in the middle of the series means it doesn't go on forever like A does. It means we have a definite end. So technically, this is a partial sum. And what's changing is the value right here. It's going from 1 to 2 to 3 to 4. So we had to figure out how to make that happen. And that meant that 1 stayed the same. So that's why I have a 1. And my n's that I'm putting in, when n is 1, it's 1. When n is 2, it's 2. When n is 3, it's 3, all the way up to when n is 10, which puts us down here at 10. So you have your daily practice on Canvas for this assignment. Make sure that you take care of that by the deadline and meet your 80% rule. And we will next time move on to another new part of a topic in sequence and series. Thanks, guys.